plus just a small number of good observations from this year. How do I get to change pages?
What space bar?
No,
The right arrow.
right arrow. No, not the down arrow.
That's great.
Drag the mouse over to the right, onto the over there, yep.
Now play. Just
Oh, there we go. This is a plot of observations, worldwide observations going back to 1993. And very obvious here, the exponential growth. The data up to 2023 is solid data. 2024, it's complete for every region except North America, and I've done an estimate from their website about what the final number will be, which is about 2,800 observations. So compared to 2020, which is only 4.5 years ago, the number of observations we've got is tripled. Huge growth. For 2025, I've done an estimate based on what's coming in from Europe and Australia and Japan. It's a conservative estimate. It could well finish up being outside the range of this plot. This is creating all sorts of challenges for the various regions as to how the reporting process works. Pardon me. And it undoubtedly is going to lead to some changes about how people report. We currently have a process where we fill out Excel forms or other types of forms, which the regional person pulls together and has to muck around with. And we now have high volume observers with single chord observations and the possibility of starting to move to a reporting environment more like when people report astrometry to the Minor Planet Centre, that the observer does a full report processing and submits just the final report to the regional person, so that for 70% of the observations, it becomes a tick and flick rather than having to do processing at the regional level. That's all challenges for all of the regions. I'll skip that slide. This is the total number of events reported by regions from 2000 until now. Just an interesting total number, 12,000, almost 13,000 events. North America and Europe are the main regions. They've got density of observers and large numbers. Australia has a small number of high producing observers. The fact that we've got more than 50% of either Europe or North America is rather surprising given the number of observers. But full congratulations to Dave Herald. Unlike the other regions, he's kept on top of the workload. Now, this is an interesting plot. It's a plot of the number of chords for each occultation. Again, growth by year. The very bottom chord in blue is the number of events where you have more than 10 chords. Inherently, those events involve travel, fairly organised, and you can see from that plot, over the 20 years covered by this plot, there has been no increase. Major multi-chord events, basically no increase. The chords, events with 4 to 9 chords Again, they require some organisation, but not a massive number of people. There's been a significant increase. When you're looking at 2 or 3 chords, the increase has gone up fairly significantly, but it's the 1 chord observations which have gone through the roof. 70% of our observations are 1 chord observations, and they're rapidly going up. And this is largely due to people with fixed telescopes in their backyard, or in the case of Bill Hanna, a remote observatory, which happens to be near me, just being able to observe whatever comes over their location. So for me, typically I'll have 3 or 4 observable events each week. In the Sagittarius cloud sessions, I will get 3 or 4 events per night. And just having the convenience of a fixed setup makes a big difference on how many you can observe. But it's the growth of the single chord observations which is stressing our whole reporting system. Multi-chord observations, they're not a problem in practical terms. 2 or 3 chords is not a serious problem. The single chord observations are where all the stress is. This is just a slide from SODIS. They moved to a new system January 23, where people report online. I'm not fully familiar with the detail of it. They've got a huge growth of observations. They've got 321 registered observers, which is interesting because a list of all observers in a year for the whole world is only 400. So they've got a range of registered observers who are clearly not having success. For the reviewers, the people that analyse the results, they've got 35 people involved.
Well,
Now, part of that is the language issue. There's probably 2 or 3 people in for English, Spain, France, Czechoslovakia, Poland, I think Italy. They're the countries I can think offhand. 4,700 objects observed over that period. Observed objects, they've got to be observations. The interesting thing, the top point there, the proportion of positive reports is fairly constant at 39%. So of all the reports they get in, about 40% of them are positive events and 60% are miss events. And that's been constant over a long period of time, apparently. So it's an interesting number in general terms. Now, this is just a simple plot of the number of chords by region. Left is actual numbers. So the figures are dominated by Europe and North America. Australia is fairly high. Japan's relatively small numbers. South America, their level of activity is a small number of people and variable activity. When you plot them out on normalised to the total number, there's some regional stats or configurations become apparent. Australia has a large number, well, in their number of observations, we have the greatest number of single chord observations. And that's because Australia, large country, low density of observers, majority of observations are single chord. You go to the other extreme with Japan, it's a small country with a high density of observers. So it's very easy for them to have a path go over multiple observers. So they have a fairly large number of 2 to 3 chords, and 4 to 9 chords, they've got, in relative terms, a huge number. Just because of the compressed nature of the country's observers. This is an interesting plot of the number of observers per event, how the number has slowly reduced as the number of single observer, single chord events has gone up. And the number of individual observers. Internationally, there's a bit of a concern about this. The 2023 number is high because of the Betelgeuse event. A whole heap of extra people involved. And the numbers for 2024 are the lowest it's been since 2017, and otherwise going back to 20 years. Don't know what that is, whether there's a heap of hidden observers to come from America where we haven't, they're still, they're only up to September last year and not processing their observations. They haven't really suffered with the workload. But that's of concern, the drop in number of observers. Satellite discoveries. Go back a few years ago, satellite discoveries were as rare as hen's teeth. Then Dave Galt and Peter Nosworthy started the ball rolling with Arecibo, and I think that was 2023. And 2024 there was 3 discovered. Oh, that's the seabed years. You can see on there the seabeds we've issued last year were 3. That's the formal announcements last year were 3. This year, so far, 2, 4, 6, 7 have had seabeds, and there's another 4 currently being worked on, and I think there might be another 1 on top of that just come in. They're becoming as common as dirt. And at the moment, a fair bit of processing effort required with those. Now, here's an interesting bit of stats about asteroid satellites. This is a table which gives the nominal diameter of the asteroid, the satellite diameter, and the separation of the centers of the satellite and the asteroid at the observation. Now, a significant factor here is when you have a circular orbit, the object is somewhere near greatest elongation for more than 50% of the time. So these figures are sort of indicative of the type of maximum range that you would expect to find satellites of these asteroids. Now, there's 2 significant things here. We've got a couple of asteroids which are relatively large diameter, but you've got all these asteroids here which are around about 5 or 6 kilometres, give or take. Now, they've only become common as an observing target in the last 18 months. It's a factor of the Gaia focused data product release being incorporated into Horizons, which has resulted in predictions which are much more accurate, with exceptions becoming more obvious. So people are now single chord observations of small asteroids. They're finding satellites quite commonly. And the interesting thing here is the stats here. So many of them right across the board. The ratio of the separation compared to the diameter is very similar across the whole lot. So that gives you an idea of how far away from the asteroid main body you need to be looking to find these things. And generally, assuming the orbital plane is roughly aligned with the ecliptic, which is a huge assumption, then it'll be along the path of motion. But there's a selection effect with all of these. The majority of these discoveries are single core events, majority, a fair number anyway. And I'll be talking, I think, in my last session about the issues with satellite discoveries. Double stars. This is a list of double star discoveries so far this year. There's 22 discoveries. Now, one of the things that we'd overlooked for decades, but now that we've had light curves coming through on a regular basis, we're now seeing and recognising events where you might have a predicted magnitude drop of five magnitudes. So you'd expect the light curve to drop right down to the bottom, but it doesn't drop anywhere near the bottom. It only goes part way to the bottom. And these are clearly an occultation of just one component of a double star. And the fascinating thing is that for these stars, we can actually generate a position angle and separation a minimum separation value with a vague position angle, which is sufficient for inclusion in the published version of the Washington Double Star Catalogue. I've had discussions with Brian Mason who manages the WDS. All the ones here with a greater than symbol are single component double stars. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I forget what's that one, the issue with it. That's 13 out of 14 out of 22 being single component double stars. We're getting to see that the number of double stars which are being detected is more than double what we were getting before, simply because of single components. And I expect probably single components will become the majority of double star discoveries in years to come. But that's 22 in the first 3 months of this year, and excludes US observations because they're not in this year yet, the reporting. So 22 by 4 is 88. We're looking at over 100 double star discoveries this year. Previous years, we're lucky to get 10. And this is raising issues of publication of these details. Now, this is just a brief run through about 6 good events, and there's nothing much I could say about each of them. This is in Japan. On each of these, I've got the light curves displayed. Having the light curves makes the analysis and assessment of these things much, much easier. When you look at these light curves, that's a nice clean light curve. Be no trouble with any light curve measuring tools to analyse that event, and it's so straightforward. You look at something like that, it's sort of gradual event on that side of it, whereas the reappearance on that side, you can get some interesting light curves there. I mean, that's not a normal type of flat bottom there. In the analysis process, and certainly when I get to see them, a quick look at the light curves will tell you which events you've got to look at closely. I mean, certainly at my stage of processing, I mean, that light curve there, there's nothing to argue about that. I can assume that the observer has analysed that properly. Whereas some of these, well, that one there, that one might have to have a closer look at. Anyway, this is one that's over this side. What's happened to the mouse? Over here, a double event there, which I think it's that observer there. The light curve isn't expanded enough to see that there are 2 events, a grazing observation there. Yeah, that's An interesting thing and clearly different from an ellipse. That's fairly straightforward. There's two shape models to it. This chord here, the fit to that nice straight edge, it's a reasonable fit. That one over there doesn't fit so well. When I see chords like that, I start worrying about whether there's a time-based issue. Time is so critical. And again, the light curves, you can see the variability of the light curves. 13 chords in Europe, that's a nice set of data there. And you can see very consistent set of chords on that side. And on this side, it's showing the same consistency. You can see quite a departure from the ellipse of the true profile of the asteroid. Again, having all these light curves, and then when you see light curves like this, which come through, they're not unusual, and that one's fairly straightforward. Partly I'm showing these light curves so people shouldn't be embarrassed about some of the, let's say, crappy light curves you get from time to time. Don't be embarrassed. Yes, that's what you got. That's your observation. And we will proudly put it up on Vizier as this is the basis of the observation, because that's the raw data that we're interpreting. And it's the real proof of what you observed. A nice elongate asteroid. This asteroid, yeah, it's interesting how that over there, chord 21 is well aligned over here. So that shape model isn't right, but there's the axis of rotation, and probably as a rotational period adjustment needs to be made with that asteroid. And that's it. Any questions?
You were talking about the single component double star discoveries.
Yes.
So that's when, just due to the alignment of the two stars, we only saw one of them being occulted. Is that correct?
Yes. The question is, with the single component double stars, is it just because we're seeing one of them? That's the case. And when you think about the situation statistically, if the separation of the double star is greater than the diameter of the asteroid, then statistically, and asteroid apparent diameters for the smaller asteroids are 10 milliarc seconds or less. So if the separation is more than 10 to 20 milliarc seconds, very small separation, the probability is you will only have one component occulted. Statistically, it's more likely to have one component occulted than both.
Yeah, I was actually leading up to my question, which was, do you think we will find, from going back to historical data, more of these discoveries, if we have the light curves available to look at?
The question is, if we go through our past observations, will we find any more? The answer is yes. I still have a data back capture issue to go through. I know on the database we have, there are about 60 past observations where the observer has noted a less than expected drop. I need to go back over those and then also send out a general note to, if people can remember observing such an event, can you dig it out and create a light curve? It's an issue which we need the light curve, so we've got a metric of the measurement. Any questions on?
Yeah, David, I've got a question if you're there.
Yeah.
You hear me?
Yes, Steve.
Yeah, it's Richard here. Just
Richard.
on the single chord, the single chord observations, and obviously they can be very fortunate to find satellites and double stars, whereas the vast majority of them are just a single chord timing on and off of the diameter of the asteroid. Are they of low scientific worth on the whole? In other words, are they contributing? Are they pulling their weight, seeing that there's so many of them that are going in and causing a lot of stress?
The short answer is yes.
Okay.
Going firstly to the double star situation, you have visual observations, the traditional observations, where the typical double star separation is down to about 1 arc second and pushing the boundaries 0.1 arc seconds. You have speckle interferometry, which can get down a bit smaller than 0.1, sort of 0.05, you're looking at less than 0.1 second, but not a great deal less than 0.1 second of arc. With the occultation observations, our separations are down around about 10 to 50 milliarc seconds. Our observations are identifying double stars with a separation which are not being detected by any other means. So it's an exclusive group of double stars. And for that reason alone, it's providing unique information about the population of double stars. When you come to asteroidal satellites, you have a different issue. You have optically discovered satellites where large asteroid, huge distance. You have the photometrically discovered satellites where they discover them by looking at light curves and mutual eclipses and occultations. And they tend to be very close together, and they have to be aligned so that you get these events. For our observations, again, we're detecting things in a different category to all the other ways of detecting them. I've sent that table, which I've displayed of the diameters and separations, to Paolo Tanga, who's responsible for the Gaia Moons project. And I commented, I think there's something interesting on a statistical side, which we can derive from that. Again, we're creating a data set of observations which is quite distinct from any other data set. So we're sampling the population of asteroidal satellites which aren't being discovered in any numbers by other techniques. So again, you're getting data, information on the overall population of asteroidal satellites which aren't being obtained by any other technique. So even though it might be just a single chord, it's very, very relevant.
So Richard,
and those single chords that have no satellites or whatever attached are still part of the deal because they're part of the population. You can get that proportion out of satellites and stars. Yeah, got it.
Now, with single chord observations generally, which they're going up, single chord observations astrometrically can be very valuable. The interesting thing is the uncertainty, so the astrometric uncertainty associated with a single chord observation is plus or minus, well, in simple terms, plus or minus the radius of the asteroid. So if you've got an asteroid which is 10 milliarc seconds in diameter, a single chord observation will give you an uncertainty of plus or minus 5 milliarc seconds, which is better than any other ground-based astrometry. And the interesting thing in particular, single chord observations on large asteroids have large uncertainty. The smaller the asteroid, the greater the astrometric uncertainty. For single chord observation, the smaller the asteroid, the better. And you finish up in a range of below 10 kilometers, I think it is. The astrometric accuracy that you get from a single chord observation is getting towards the type of astrometric accuracy they're getting from a single Gaia asteroid measurement. It's do not underestimate the value of single chord observations of small asteroids. They're very valuable.
So, Richard, I just want to see.
Okay, great, thank you.
Just want to add a couple of extra comments there. I'm sort of foreseeing a future coming up where observers split into two different sorts of roles. There's those of us who, and I'm probably in a worse situation than most people, being geographically separate from other observers by a long way. Almost all my observations will be single chord. I've got to drive a long way for it to be otherwise. Those people doing single chords are effectively screening the whole pile of asteroids for discovery of doubles, whereas other group of observers who are probably seeking to confirm suspected doubles will need to travel. So you've got quite different niches and strategies, and people can choose and be a bit of both, but that doesn't devalue either of them. I'd also make the comment that whilst Dave's graphs show this alarming increase in single chord observations, that's probably the statistics that's led to the discoveries that we have. You had to do all those in order to detect the ones that we found. And so
yes,
I think there's a link there, and don't give up if you don't see another dot on your occult watch line because there's no one else watching. You're still doing, it's a different role. There are different roles differentiating out of what observers can participate in.
On that core issue there in the growth, Japan had an issue with backlogs or the workflow, and they actually, at the end of last year, they proposed and agreed amongst the group to limit observations to not include small asteroids. And when I pointed out to some relevant key people that, hey, that's where we're discovering the satellites and a range of other things, they got rid of that process, and they've finished up changing their whole processing scheme so they can actually handle the work.
We have to adapt. Don't
Yes.
forget that we have to adapt.
Yep.
Okay.
Thank you. That was a great answer. Thanks, guys.
Ray's calling time out.
I think so. I can't remember what schedule says.
The schedule has this going through to 10:20, so Dave can ramble more. I finished early, but Dave can ramble more if he wishes to.
Thanks for recent discussion on forums about the accuracy, supposed accuracy of predictions, particularly for small asteroids. So anyone who's been observing recently will know that suddenly our feeds went from having 2 to 3 to 5% to having 100%, 0%, 100%, 0%. We've all had to adapt. So there has been questions about those smaller ones. So I'm just wondering if the discrepancies between the prediction and what we actually observe is enabling a deeper modelling or understanding of asteroid orbits and the influences on those orbits. Is there new science that is being encouraged by these observations?
I have a view about a cause of that discrepancy, which is probably, well, Paolo Tango sort of partly disagrees with me on this, and he knows more about Gaia than I do. I mean, he is the person that analysed the Gaia data, get the asteroid astrometry. There are some interesting issues. I'm aware that when they ingested the data into Horizons, they had some concerns about the data, and they did have an interest in having some feedback on the issue of how accurate they were. I tried doing something about that 18 months ago and nothing much happened. We need to be doing something about that. In terms of the value of the small asteroid things, there's a project that I was invited to join 12 months ago, which has been put on hold. There's so many other things going on. It's a project being run out of Horizons, where the aim is to use the precise astrometry associated with the Gaia astrometry of asteroids, combined with occultation astrometry, to try and detect the mutual effects, the gravitational mutual effects between asteroids, to shut up the people out there.
You were powered.
The astrometric precision that comes from the Gaia data and the astrometric precision of our occultation data seriously opens up the possibility of measuring the gravitational interactions between asteroids, allowing a measurement of the mass of a significant number of asteroids. And that's something which is still being worked on, to be developed on, but our occultation astrometry is seen as a significant input to that process. I mean, I can't emphasize too much about how significant our astrometry is. That's where, yeah, I'll shut up.
Thanks for that, Dave. I've no idea that particular type of science was there. I've just got an observation that, any time there's some instrumentation or technique that allows greater accuracy, new science follows. Our occultations have potentially amazing accuracy. That's really only limited by the signal-to-noise ratio and star background we've got. And we haven't yet reached the limits of the potential usefulness for occultations. So there'll be other things that are coming up. That's really interesting and really encouraging. But even though we've had the Gaia missions and the James Webb stuff there, and all these really fantastic observations, little telescopes all the time, and are still able to contribute to scientific discovery.
Can I suggest that when people are speaking from the room, they've got to speak. Think about talking
around here.
Well, again,
Just put your voice towards that.
yell very loudly.
Yes. You've got to make somebody on the other side of that screen hear you.
That's right.
The next presentation I do, which is a sort of a semi-repeat of what I did on the thing, I've got an interesting plot in there about the accuracy of the astrometry from our observations, just putting it into context. And if you're not impressed by it, then go and do something else.
Very good. We might, if there's no more, that session was meant to end at 10:20, but that's fine. We've got a break now for morning tea, resuming at 10:50 New Zealand Standard Time.